In our energetics topic, we try to work out how much energy is involved in bonds and then how we can use this to work out the energy changes in any sort of a reaction. This little session is going to concentrate on the bond energy questions, and these are mandatory for our component of the guide. So I'd be suggesting there would be questions in paper 2 for sure, and maybe some questions in paper 1 as well. In our bonding unit, we learned that bonds contain energy, and we need energy to break the bonds, and we can actually work out the size of this. And obviously the more electrons are involved in a bond, for example, having 4 involved in a double bond as opposed to 2 in a single bond, means there's more energy involved in breaking it. But we also saw that the bonds were shorter. The more electrons involved in it, the shorter our bonds get, so the bond length decreases. And we know that the energy is needed to break these bonds, as we understand. A nice simple way of thinking about what we're doing is actually this little diagram here, where we can see that we need to break bonds, so we need to put energy in, and although it's counterintuitive, we actually need to give energy, or energy is released when bonds form. And it's sort of semi-counterintuitive, but that's neither here nor there. So what I'd like to think from this is we start off with molecules. In other words, bonds are present. We break it, so then there are only atoms present. So down here, there are bonds. Here, there are only atoms, no bonds at all. So we've broken it. That's the amount of energy we've used. The energy up the side tells us we're using energy, this one. When these reform, right, we actually release energy. And get this. Now, an interesting thing we've got here is there is a difference between the levels of where we started off with our reactants and where we came with our products. There's actually less energy in our products than there was in our reactants. So we say that there has been an enthalpy change and there's been a negative. If the line was up here above where the reactants are, it would be positive, but it's below, so it's a negative one. And that's classic of an exothermic reaction. So one of the things we need to do for our exams, and one of the things we need to know how to do for exams, is to use bond energies to work out how much energy changes there are in a chemical reaction. So let's look at what we should know. So we've got that we need to add energy to break bonds, and breaking bonds is an endothermic process. So endothermic means energy is put in. We need to release energy to make bonds, so making bonds is an exothermic process. As we'd expect, making and breaking should be opposites. All right? So what we can do is we can say that the enthalpy change, in other words, the change in energy that's involved in this process for any particular reaction, equals how much energy I need to break the bonds minus the energy I need to make the bonds. Let's consider an important industrial application. And we've got a thing called the Haber process, which involves the making of ammonia. Now, ammonia is used in 2 very, very important things. One, of course, is fertiliser for making food, and the other, of course, is making munitions or bombs and explosives. And so we can actually see, as we go further on, the process involves combining nitrogen gas with hydrogen gas to make ammonium gas. And as we'll see when we get to equilibrium, we have to do things to make the most money out of this. But that's another story. So we should be able to work out, if we know the energy involved in the bonding, we should be able to work out the enthalpy change in this reaction. So where do we go? Well, table number 11. Our table tells us what's going on. Now, our reaction said we had 1 mole of N2 reacting with 3 moles of H2. Now, we know that the N bond, now I've only written it as N single bond here, but we know that the bond in ammonia is a triple bond, so it's going to be quite a bit of energy we need to break it. The single bonds for hydrogen we need 3 moles of it, so it's going to be 3 times whatever it is per mole, because the energy we're given in our data book in table 11 is in terms of kilojoules per mole. So don't forget to multiply them out. So if I add the numbers, and I can see that the NN bond, the NN triple bond, is 945 kilojoules per mole. The HH hydrogen bond is 436. Now that goes with probably what we've been talking about, in the fact that hydrogen single bonds are weaker or require less energy than multiple bonds like nitrogen. So if I then do the math, I see that in breaking the bonds I'm going to require 2253 kilojoules. That's quite a bit of energy involved. Then if I do the next process, I'm going to try to work out what goes on with making the bonds. Now each NH3 has 3 N single bond H bonds. So that means I've got to make 3 moles per molecule of those bonds. So that for 2 moles of NH3, I've got to make 6 moles of NH bonds. And that's where those numbers come from. So if we then do the sums, we find that each one of the NH bonds is 391 kilojoules. So I see that total in making the bonds, I have released 2346 kilojoules. So in this case, the total enthalpy for my reaction is going to be equal to break minus make, which is 2253 minus 2346, or minus 93 kilojoules. So from that we know that the making of ammonia using the Haber process is exothermic. We've got the negative sign here. And it requires, because we've got 2 moles in our reaction, I can't really say per mole. It's actually for the reaction. Our enthalpy of reaction is 93 kilojoules. And we've got the negative sign here to show us that it's an exothermic process. And I'm sure we'll remember that for a long, long time.